For like super silly, the question is like pretty broad. It's been too really specific. Yeah. And I just like didn't start.
I've been seeing it now as I'm talking to Okay, I've been there.
So silly.
Well, there was I feel like these
I remember seeing her.
I didn't choose it.
Yeah. It's like when there's like.
Yeah, but it was just like there's like it would be like how something attaches to like it would be so specific to a certain like a certain immune system, or that it would be like I honestly don't understand like because I like the practice yes, the yeah, that makes sense. I feel like it's just Russian. Yeah, that totally
Okay, I know it was. I just wrong.
Well, I mean, it was those ones were kind of odd, but like it was more like there was specific like parts of the immune system that needed that function, and it wouldn't have been that involved. Also, the margin, like I think there was like I can't remember the name of it, but there was something on there that was like a definition or something. I was like, yeah, no, yeah, it was also kind of hard. I didn't have it for I was just stuck. I don't know, after that test, I was even like yeah, after that, I was like, there were so many questions that I had questions that I had. Okay, it was
Well, I would say I'm pretty much
I was just like, I'm not very into the saving, and even if I'm like, I know the material, I'll still everything here, so. Yeah, I was kind of just, yeah. Honestly, I want to know just so that I can consider. I wonder if she was because I just know.
It's like the
Yeah. I just didn't know like when this is gonna happen, so it was
the front right wheel is up in the air.
So, any of you look at those problems? You okay with them? I'm gonna go over this energy stuff a little bit more. Some of you did look at them. I'm getting one nod. Been here a couple of times, all right. So let's go over this. This is kind of a decent little summary of the logic and facts. So if we're talking about equilibrium, and we're looking at 6.43 here. When K, so is that K, this A here, the greater than 1 or less than 1? It's greater than 1 by a good bit, right? So that favors products, meaning there will be much more product than there will be reactants in the reaction vessel at equilibrium. This isn't always true, but this book seems to want to just treat this as true. But so I put it up here. This is showing a negative delta H. This is your negative delta H. here's the reactants, here's the products, the energy went down, so that's a negative delta H. So you could, I think you can, I guess, by the way this book does it, is favor the products. Negative delta H. So you can think of it like this. When this one is lower than this one, we favor the products. When this one is lower than this one, we favor the reactants. And then the next two, K greater than 1 or less than 1. Less than 1, so this one, if you have a K less than 1, you favor the reactants, not the products. And when this is positive, you favor the reactants. Okay, so just a couple of those. Let's do these. So let's look at 6.53. So here's our reaction and here's the K value. I guess I'll do this, but to write the expression to calculate K, I tell you guys to think so amount of products over amount of reactants. But really the way you calculate these is you need concentration of H2 and the other product is Br2 and HBr. So you do that and then you use the coefficients there as powers. And that's the only one there. The other two are 1. So that's how you would write the expression. This is just a more specific thing than this. This just means in general, and that's really all you have to remember for most of these problems. The products are on top. Are the reactants or products favored in this equilibrium? How do you tell?
Products, because the K is greater
Is that K greater than 1?
than 1. No, never mind.
It's the opposite.
Yeah.
It's a very small number because of this negative on the 20. So we would move this decimal this way. So it's a very small number, so is it products or reactants? Reactants. Do y'all see this? So would you predict delta H positive or delta H negative? We're favoring the reactants, so we're here. So we can predict delta H positive. Are the reactants or products lower in energy? Well, if we're here, then the reactants are lower in energy. That's the reactants. You with me? Would you expect this reaction to be fast or slow? It's a trick question because you can't predict how fast this reaction is from the information given. If you wanted to speed up a reaction, you could increase the temperature, but usually the way its energy of activation is this. You need to lower energy of activation. catalyst to do that. So you would lower the energy of activation to speed it up. Or you could heat it up. That would speed it up too. All right, let's skip A, write the formula. Are reactants or products favored in 6.54?
Reactants.
What are you looking at to answer the question? The value of K. And what are you trying to, what are you looking at? What about value of K?
It's greater than one.
If it's greater than 1, it favors products. And this one's greater than 1 by a good bit, so we're here, greater than 1. So all these facts go together. So you expect delta H to be positive or negative? Negative. Delta H negative. Reactants or products lower in energy. Here the products are lower in energy. You guys see this? A few more of these. Okay. So our reaction is 3 moles of O2 and 2 moles of O3. They're both gases. All right, so if I pull out some O3, so I've got it sealed up in a chamber, but I'm somehow able to reach in there and pull out some O3. Right after I do that, what happens? What effect does each of the following changes have on the direction of equilibrium? And I'll put gas here because that's going to matter. Okay. O3. I remove some O3, and then what happens to the equilibrium? This is Le Chatelier's principle. If I remove some of this, equilibrium will shift this way. If I add some of this, equilibrium will shift that way. If I remove some of this, equilibrium will shift that way. If I add some of this, equilibrium will shift that way. So if I decrease the amount of this, which way does it shift? Left or right? Decrease the amount of this, which way does it shift? To the right. I remove some of this, we shift towards it. I add some of this, we shift away from it. If we decrease this, decrease some of this, left or right. Decrease this. If I decrease this, we shift towards it. If I add to it, shift away from it. If I remove some of this, we shift towards it. If I add some of this, we shift away from it. So if I decrease some of this, take out some of this, if you remove some, you shift towards it. If you add some, you shift away from it. So if I remove some of this, it shifts left. If I add some of this, it shifts right.
So it's the same on both sides.
Yeah. If I remove some of this, shift towards it. If I remove some of this, shift towards it.
Is that because it's trying to get back to
Yeah.
equilibrium?
It's going back to equilibrium. The shift happens so that it can get back to that equilibrium. let's say K equals 100. And then I remove some of the reactant. When I remove some reactant, that suddenly decreases this. So if I remove some of that, what happens is that gets a little smaller, and now K, but I'll put it in quotation marks. The answer to this problem will go up a little bit. Let's say it goes to 110. But K is still 100. What I've just done is knock it off of equilibrium. So once I do that, in order for this to get back to 100, some reactant needs to become product. Did I say decrease this? Yeah, I said decrease this. What happens is some products have to become reactants in order to get this 110 back down. So then we decrease this while we increase this, and that will decrease the 110 back down to 100. And saying some products need to replace those reactants that I removed. That's the same thing as saying go this way. Maybe that helps. What have I not done? If you decrease the temperature, all right. Now that we're talking about temperature, they tell you up there, consider the endothermic conversion. So they're telling you this is endothermic. Endothermic. Put heat on the left. So I told you guys the other day, the book doesn't do this. This is just always the way I teach it. Just pretend heat was part of the reactants when it's endothermic. And now we can do the same thing. If I add heat, we shift that way. If I remove heat, we shift this way. So it's that same sort of pantomime I'm doing. That's why adding this, I think, helps. Adding heat is the same as raising the temperature. Removing heat is the same as lowering the temperature. But put those pieces together. If you decrease the temperature for this reaction, which way does it shift? Left or right? Decreased temperature means remove heat. So that's going to make it shift this way. If you add a catalyst, catalyst doesn't affect equilibrium. Catalyst won't affect K. Increase the pressure, okay. You look at the gases, and this has 3 moles of O2, and this has 2 moles of O3. If you increase the pressure, well, I told you guys, for pressure, you can put a P, again, just a mnemonic, just like me putting heat here. But P for pressure, you put it on the side that has the most number of moles of gases. This one has 3 moles of gas, this one has 2. So now, add pressure, that is increase pressure, we shift that way. If I decrease pressure, we'll shift this way. You can make this exists in the reaction vessel and this exists in the reaction vessel. If you increase the pressure, it's just sort of like it's trying to compress into the smallest space it can. So it takes some of these and turns them into these, getting rid of 1 mole of gas. So increase pressure, which way does it shift? To the right. Yeah, let's do this one so I can make this point. Because I don't think I've said that one yet. But all right, looking at H2I2 and HI. gas. That's a gas. Alright. So, if I decrease the amount of this, which way does it shift? Remove some of this, which way does it shift? Shifts to the right. Remove some of this, we shift toward it. Add some of this, we shift away from it. Increase the amount of this, which way do we shift? To the right. To the right. Decrease the amount of this, which way do we shift? To the left. If I decrease the temperature, so it says this is exothermic. If it's exothermic, then it's sort of like heat is a product of the reaction. All right. Decrease the temperature, which way do we shift? Left. Remove some heat, shift to the right. Remove some heat, you shift to the right. Increase temperature, add some heat, we shift to the left. Is this starting to click? Okay, increase pressure. There are cases, how many moles of gas are on the right side? 2 moles of gas total on the right side. How many moles of gas are on the left side? Yes. How many moles of gas are on the left side? There's 1 there and 1 there. There's a total of 2 moles. And I haven't said this yet, but maybe it's obvious when I say there's 2 moles here and 2 moles here. There's no advantage shifting either way if you increase or decrease pressure. There's 2 moles on both sides. So actually, pressure has no effect on this. Increasing and decreasing the pressure won't shift the equilibrium one way or the other. Do you see why? You can't compress it. Compressing won't shift it, and releasing pressure won't. So the changing pressure for this reaction will have no effect. Question?
So why did pressure affect the other one though?
The other one had so here, increasing the pressure, sort of trying to compress it, it gains an advantage by turning some of, it was O2. These were gases. So compressing it makes it want to shift to the side that has less number of moles of gas.
So it doesn't matter what it doesn't matter that the equation is technically balanced, it just matters not what the side how many moles it has.
Yes, for this, all that matters is the number of moles of gas
Okay.
on either side. You just add up the total moles of gas on each side. This has 2 moles, that has 2 moles, so that isn't affected by pressure. But here, if you're trying to compress it, it wants to shift this way, so it takes up less space. And if you release the pressure, it allows it to expand in more space. So it's possible for pressure to have no effect when the number of moles on both sides is the same. All right. Look at 6.67, same types of questions. Somebody threw the fan down the stairs. Okay, so what do you think for A? Increase the amount. So increase the amount of this, what's it gonna do? Shift right. If I decrease the amount of this, what's it gonna do? So it's left. If I decrease the amount of this, shift right. Decrease the pressure, all right. There's 1 mole of gas on this side and 2 moles of gas on this side. So if we decrease the pressure, which way is it going? Left. If I increase temperature, they told us it's exothermic. So you want heat written in on the right. So I would have heat over here. No, over here. So increase the temperature, add heat, which way does it shift? To the left. If I have heat over here and I'm adding it, it shifts away. And decreased temperature is the opposite. So it's heat away, it shifts to the right. Do you see why I put heat on the right? It says it's exothermic, so put the heat on the right. It's as if heat is a product of the reaction when it's exothermic. Heat comes out. When heat goes in, it's like heat was one of the reactants. If you're putting heat in, it's like heat was a reactant. Okay. I think that's all I have to review of this for you to be able to answer these questions. So the questions I have online, if temperature is increased, a reaction that yeah, I think y'all can answer all of these. If you stumble across one that you can't, email me or bring it up at the beginning of class. But I think I'm done with that chapter. Okay. To start our new information, in chapter 7, so I'm probably not going to follow the book very closely for this. One of those things that I have my own way of explaining. I think the book just makes it seem way more complicated. You guys have any questions? So this is an equation we can use. Let me write real big over here. This is when we're dealing with gases. That and strictly that, this equation. It's called the ideal gas law, or the ideal gas equation. An ideal gas, into mostly these binary compounds. Any of the noble gases, basically any of the very small molecules that are gas in its gaseous state are what we call an ideal gas. These are all ideal gases. They're ideal because one, you spell negligible. It's misspelling the word. But they're so small. So we talk about a gas occupying a volume. But you have your volume that the gas is in, but those little particles do take up a little bit of space. So somewhere in that volume, there are these little gas particles. As long as it's very small though, whatever the volume of that space is, the volume that you're looking at, that you can calculate, that you can measure, you can assume that these little things are infinitely small, and that all that volume is taken up by just space. That's one of the assumptions. Two, if these were charged or very polar or something, they wouldn't be considered an ideal gas because they're attracted to each other. So we neglect any attraction they have. They do have a tiny amount of attraction to each other, but it's very, very small. So just realize not every gas you can treat this way, but we have this word, the ideal gas, to refer to these that you can treat. What I'm saying is you can use this very simple equation to predict variables for a gas, as long as it's an ideal gas. You use a modified version of this for larger gas particles or particles that have attractive forces between each other. But we're going to stick with this. And I know I haven't told you anything about that, but I just want to introduce the idea of an ideal gas before I start showing you how to do these calculations. So PV equals nRT. P is pressure, V is volume, N is number of moles, or you can think of that generally as the amount that's there. T is temperature, and we have to do this in Kelvin. R is just a constant called the gas constant. Okay, and I forgot to put temperature conversions on our first test, but we did go over them. But just as a quick reminder, if you had 22.3 degrees C, you can convert that to Kelvin by going 22.3 plus that magic number, 273.15. I'll give you that on the test if you forget it. But that converts Celsius to Kelvin, and you have to be in Kelvin to use this formula. So the temperature in Kelvin here is 295.5. So 22.3 degrees C is 295.5 K. So I'll mention that again, since I kind of walked away from temperature conversions a couple months ago. So this has to be in Kelvin. There's more than one R constant. The two you'll need for any problems here. Notice this one is in liters, atmosphere. Most of the time, your pressure units will be atmospheres. There's a few of them though. I should learn how to bookmark. It's a little galling, but there's just kind of a ridiculous number of pressure units. Here they are. Every one of these is a different way of measuring pressure. Most of the time we'll use atmospheres. I think all the questions I do will stick to doing either atmospheres or millimeters of mercury. But that's torr, that's pounds per square inch. Pascals is another one. So anyway, I don't know why there's so many different ones, but so let me, and I don't mind giving you any conversions, but I feel like that gets us away from the heart of the subject, converting between all the different ways to do pressure. Okay, so this is section 7.5. This is really where I'm starting with this. I reintroduced Kelvin, and somewhere up there it introduces all the different pressure units. But I want to keep these. We have an R value of 0.08. Show these. And I'll give you these constants on the test. You don't have to memorize them. 821. And the units are liters, atmosphere, mole, Kelvin. Liters, pressure in atmospheres, moles, and Kelvin. And R is this constant. And then R equals, this other one's 62.4. And the only difference here is that means millimeters of mercury. And some problems will give you pressure in atmosphere, and some problems will give you pressure in millimeters of mercury. And that decides which one of these you're going to use to do a calculation. But you'll see what I mean after I do some of these. So I don't mind giving you PV equals nRT, the formula for the test. I don't mind giving you the R values. But let me show you what this does in terms of calculations. So going to the problems at the back of this chapter. when you approach one of these types of problems, okay. If you write that down at the beginning of one of these types of problems, I can make these easy, at least easy to me. All right, there's two states. There's a starting state, and then something changes, and then there's a new state. That's what the ones and the twos mean. This is saying, and you figure out the state really from context. If a balloon containing 2.2 liters of gas is at 25 degrees C, and then it's cooled to negative 78 degrees C, what's its new volume? All right, let me fill in some blanks here. State 1 is 2.2 liters and 25 degrees C. Just 25. If I had 25, it's 5, 6, 7, 8, 9. So converted to Kelvin, 25 degrees C, temperature is 298. T1 is 298.15 K. And volume 1 is 2.2 liters. And then it says, it gives us a new temperature, cooled to negative 78. But ultimately, we're subtracting 78 from that. 9 minus 7 is 2. So temperature 2 is 222. I take that back. There's nothing after the decimal here. And this is addition subtraction rule. So I have to do that. So we should really just be at 298. Okay, and this should just be 220. And then follow the significant figure. Okay, that's all the information we've been given. There's nothing else up there that I could fill in. It doesn't give us a pressure anywhere. It doesn't give us a number of moles anywhere. And the new volume, I'll put a question mark here. That's what's being asked for. You see that? The key to answering these types of problems is deciphering what you're reading and filling in these blanks. Okay. Anything that's not mentioned, assume it stays constant. All right, if you can get that far, the rest of this is just a bit of algebra. The algebra is start with PD equals nRT. And what you're going to do is use algebra to get the things that stay constant. You want those on the right, and the things that are changing put on the left. This is changing, and this is changing. And the things that weren't mentioned, we're assuming those were constant. So I've got to do the algebra necessary to get pressure and moles on the right side, and volume and temperature on the left side. Okay, so I want to get pressure on this side. So I'm going to divide both sides by pressure. And that'll give me and now I need to get temperature on the left side because it's volume and temperature that are changing. I can do that by dividing both sides by T. which gives me V over T, N, R, there. Now I have the things that are changing on the left, and the things that are staying constant on the right. You with me? And now, to answer this question, we're just going to take this, and we're going to go V over T equals V over T. These are 1s, these are 2s. And now let's just plug each other. We have 3 out of 4 of these variables we can solve for the 4th. We're solving for V2, so I would multiply both sides by T2, which would give us V1 times T2 over T1 equals V2. And that's it, you just plug in the so volume 1 is 2.2 liters. Temperature 2 is 220 K. And temperature 1 is 298 K. The K's are going to cancel, we'll end up in liters, but that's what we expected. Two divided by 298, and I get 2 significant figures because of this. My calculator says blah, 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 but we're keeping these, so it's okay, let's look at the next one, 7.38. All right. How hot must the hot air balloon, how hot must the hot air in a balloon be heated if, okay. Can you tell that's asking us for a temperature 2? Hold on. If it, let me read it to be sure. Okay. Initially, it has a volume of 7.50 liters at 20 degrees C. So, what do I put where over here? Do I have a pressure anywhere? There's no pressure mentioned. Initial volume. What is it? 750. Um, 20 degrees C plus 20, 7, 8, 9, so 293.15. I'm going to assume they meant that, so we have at least 2 significant figures. So it's 293. So that's our initial temperature. And then it says, and the final volume is 1,000 liters. So final volume is 1,000 liters. And it must be asked. So how hot must the air balloon be? That's the same thing as saying what would the temperature be? And we're going to get it in Kelvin. So this is what we're looking for. That's the only really thinking part about this, doing your own critical thinking. The rest is just like I did before, the same thing about algebra. So these are constant. So it's this changing and this changing. So now I need V and T on the left side, and I want everything else on the right side. All the stuff that stays constant. R is always constant. It's the R constant. So I would, let's see, to do this, divide both sides by P, then divide both sides by T. Divide by P, that would give us V equals. And then divide both sides by T. And then the last step is to bring this down. And then you can just plug into it once again. We've got 3 out of 4 variables, we just solved for the 4th. Good, this one does pressure. So 41 and 42. So 7.41. So we start like that. So what are we given here? Okay, tell us what an autoclave is. An autoclave containing steam 100 degrees C and 1 atmosphere of pressure is then heated. What is the final pressure? So what is what's the initial temperature here? 100 degrees C, but we have to do this. We add those up. So 373.15. But this 100 doesn't have anything after the decimal. Yeah, you did that. Good. So we have to just keep just this. All right, what else do we have? What else should I put where?
There's pressure.
So 1.0. And we should have at least one more number. 150 degrees C, so we have this, but it's 150. So 423 K. And this is what we're being asked for. What's the new pressure? Assume these are constant. So it's these that are changing, P and T. So I want P and T on the left side, I want everything else on the right side. To do that, divide both sides by T, and then divide both sides by V. So divide by V, divide by V. And it's P over T. And then the last step in this bit of algebra and you just plug and chug. And you get your answer in atmospheres. That's the process. All of these types of problems are like this. 1.42. Let's see. So this is also pressure and temperature. So it's going to be this. But can you fill in things where they go? I can go ahead and write constant on those because the amount of the gas is not mentioned and the volume is not mentioned. Initial is that needs to be converted to K. Final is 80. But that needs to be converted to K. And you would use this same, because you look here and you go, it's pressure and temperature changing. So you do this and you find that. You guys okay? The key is just peeling the information out and getting it filled in. Then anything that's not mentioned, you assume is constant. This is one that'll have 3 variables. So I'm looking at 7.43, but they don't give you this as a word problem. They just throw some values at you. But this one would say something like, a sample of gas is at this pressure and this much volume at this temperature. And then later, its volume is this and its temperature is this. What's its new pressure? P2 is what we're looking for. And we're given 0.55 atmospheres. 1.1 liters. 340K. I look at the wrong one. Oh, well, I'm down here. I don't know why. I thought I was going to do that one. 3.0298. They don't mention moles at all, so assume that's constant. So now you do this. So now we have 3 things changing. So these 3 things we want on the left side, and we're going to get N and R on the right side. N and R on the right. So all we have to do is divide by T. And then we're working with this. So now we have 5 out of 6 variables. So we plug in the 5 variables, solve for the 6th, using our algebra skills. With me? All right, there's one more angle with this PV equals nRT. And that's where these come in. And that's when things aren't changing. You don't have a 1 and a 2, state 1 and state 2. You're just calculating something about one state. PV equals nRT. How many moles of gas, so we're looking for N, contained in human breath that occupies 0.45 liters, 747 milliliters of mercury, that's the pressure, and 37 degrees C. We've got volume, we've got pressure, we've got T, but I've still got to convert that. 273.15 plus 37 is 10, it's 11. So this is
Yeah, well, normally when I do those, I don't ask, so I figured, like, you know, this is like the one video, not video. Like,
all we're missing really
I'm
is
messing up. This is like the
moles.
one,
and R is
I don't
always
even know what I'm going for, so I'm lost.
going to be one of these. And since we're in millimeters of mercury, we're going to use this one.
I
So
think
R
I think
equals
W F after that.
62.4. And now we have all the variables we need to solve for N. So now it's just algebra. I would go ahead and divide both sides by RT, and then you just plug everything in. And 47 millimeters of mercury. Volume is 0.45 liters. R is 62.4 liters, millimeters of mercury, Kelvin. And then what? Temperature, 310 K. And these units will crunch down to moles. This goes on calculator. Seven 47 times 0.45 divided by 62.4 divided by 310. Calculator says 3 significant figures, that's 2, that's 3, and this is actually 3? Yeah, that's 3. So we need 2 significant figures, it's that, so 0.017 moles of gas were in there. But, and notice, nothing is said about any changes, state 1, state 2. That's how you know you're just going to use this just as a raw equation, and you're going to need an R value. And I'll give you these on the test, you don't have to memorize them. I'll give you that on the test.
So you don't have to calculate out the times
All of the, you mean cancel the units?
like with the R value, you just use the 62.4. You don't have to figure out the rest of it.
You mean the rest of it?
Like, do you have to plug in numbers for the liters times?
No. No, this is just like 12.01 grams per mole. What that means is 12.01 grams over 1 mole. This, I guess, doesn't really have that same interpretation because there's 2 units here. But these are the units of R. Let me show you this. P in atmospheres, V in liters equals N, which is moles, R, which is in atmosphere. These will do liters first. Liters. That's the units for R. T unit is K. If I divide this side by N and T, I can make it go P in atmospheres, V in liters, N in moles, P in Kelvin equals R. And if I split these out, pressure, volume, so if you take these 4 things and do the math, you're going to end in units that are atmosphere, mole, atmosphere, liters, mole. So R itself, there's not really like a physical interpretation. It just needs to have those units, so it ends up with those units. I didn't bother to calculate that, I guess. But these types of problems are like that. Just notice there's no change. For these types of problems, so R is always a constant. It's always the same value. So really, there's 4 variables that you need to be given, or no, you need 3 out of 4 of those variables to solve for the 4th. Does that make sense? So problems like this are going to give you 3 out of 4, whichever 3, and then you use that equation to solve for the 4th using the appropriate R value, one that's got the right units for it. And another hallmark of these is there's nothing about a change. There's nothing about a state 1, state 2, this temperature, and then later this temperature. You'll just be given 3 out of 4 of those values and you solve for it. That's our first foray into chapter 7. I skipped all this stuff because my way is superior. They introduced these. I still hate this about this. I hated it when I was a student too. Let me find this chart. So there's Boyle's law, Charles' law, Gay-Lussac's law. Let me get to the chart that's got them all. And I just think there's no, PV equals nRT. Really, they go through all these chapters just to show you that the overall equation is PV equals nRT. But if you know that from the beginning, I mean,